Section 2.8, the derivative as a function. First, let's consider a problem from section 2.7. This is number 11 from the exercises in the textbook. Part A, a particle starts by moving to the right along a horizontal line. The graph of its position function is shown in the figure. When is the particle moving to the right? When is it moving to the left? And when is it standing still? So essentially we have a horizontal line and we have a particle, let's say it's this blue dot, and it's going to start moving, and it does that by moving to the right, and then maybe it moves back to the left, and then maybe at some point it's standing still. If we look at the graph that we have in front of us, we can see that the red line is essentially telling us its position at any point in time t. So position here is measured in meters and time is measured in seconds. The first part of this graph is a line that is going up and to the right, which means as time is going by, the position of this particle is moving away from where it started. So the first line that we see here, this piece, that's telling us that our particle is moving away from where it started, which means it's moving to the right, because that's what we were told how it starts moving. So we definitely have that it's moving to the right, starting at time equals 0 seconds, and then ending at time equal 1 second. So we've got from 0 to 1 seconds. We also see that there's another place where the particle is moving to the right, and that's the other part of the graph where it's increasing. It's going up as it's moving to the right. Here this is just from 4 seconds to 6 seconds. So then when is it moving to the left? Well, that would be the opposite. When the graph of our position as a function of time is going down and to the right, because there it's heading back to where it started. This is from 2 seconds to 3 seconds. And then finally, where is it standing still? That would be where we see these horizontal lines, because the position is not changing, it's just staying where it is. So this would be from 1 to 2 seconds, and also from 3 to 4 seconds. Okay, so that's just understanding the graph of the position function. So now, how do we graph the velocity function? One key point from section 2.7 is that the velocity function is the derivative of the position function. So we can even think of this as if s of t, which is what we have here, is the position function, then s prime of t, the derivative of that, gives us the velocity function, which we indicate as v of t. So that's one thing that we had in section 2.7. But also, the derivative gives us the slope of a tangent line. So we can combine the idea of the derivative gives us the slope of a tangent line, and also, if we're talking about the position function, the derivative gives us the velocity function. We can combine all this together by considering the slope of each line that is present in the position graph. So, for example, the slope of the position function. Notice that the slope changes, right? We don't have just one line. We have many lines that are pieced together. So for example, in the interval 0 seconds to 1 second, the graph goes up 3 units and then over to the right 1 unit. So the slope is 3 over 1, which is just 3. If we then look at the next piece, which goes from 1 second to 2 seconds, this is where it's standing still. Notice that the slope, there is no rise to that. It's a horizontal line. So it's 0. And technically divided by 1, but that's still 0. So then we continue in this same manner. The next part is the green part that I've highlighted on the position function. Here it goes down 2 units from 3 to 1. So from 2 seconds to 3 seconds, it goes down 2 units, but over to the right 1, so that gives us -2. And then for the remaining parts, from 3 seconds to 4 seconds, again it's standing still, the slope there is 0. And then finally from 4 seconds to 6 seconds, it goes up 2 units, but then also over to the right 2 units. So 2 divided by 2 is 1. And so what we just got here is, over certain intervals, the value of the velocity function. This gives us another piecewise defined function. So as a function of t, and we can just use the values that I have here. I'm only looking at from 1 or 0 seconds to 6 seconds. So there's my 6 seconds on the t-axis. And then I have particular values for my velocity. We go down as far as -2. We also go up as far as 3. So from 0 seconds to 1 second, we have the value of our velocity is 3. And this would just be a horizontal line. That goes from 0 to 1. And then the next horizontal line would be when we had that our slope was 0. That goes from t equal 1 second to 2 seconds. Now already what I'm doing here is I'm drawing a piecewise defined function, so I should be careful with where I have closed circles and open circles. And I would say that we can kind of take this assumption that we don't have an instantaneous velocity right at the beginning. Maybe it has to accelerate. So maybe just to err on the side of caution, we should keep some open circles on these endpoints. What's more important is that we're just thinking of the velocity as a function of time. So then from 2 seconds to 3 seconds, we get a velocity of -2. And then from 3 seconds to 4 seconds, again, we have a velocity of 0. And then finally, from 4 seconds to 6 seconds, that's where we get a velocity of 1. And so that's our velocity graph. Notice here that we've got these breaks along the way. That's something that we want to remember as we take a look at some later examples. But the key takeaway from this is that the graph of the velocity function relates to the slopes that we recognized in our position function, the rates of change in that function. So what we do now in section 2.8 is we write the derivative as a function, which simply means taking the a that was the derivative at a point in the definition in section 2.7 and replacing that with an x. So that is simply just written here. F prime of x, meaning the derivative of f of x, is equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h. The derivative function is simply a model of the slope of the original function f. So as x changes, the input, the slope of f of x changes, and those changing slope values become the range of f prime of x. And that's exactly what we just saw in the example above. So now let's look at another example. Number 22. This comes from page 162 in your textbook. Find the derivative by using the definition, meaning we're going to use this definition. State the domain of the function, meaning what are we allowed to put into the function, and also of its derivative. So we'll find the derivative first. Since I have y equal mx plus b, I'm just going to write y prime. If I would have had f of x equal mx plus b, then I could write f prime of x. But I've got y, so I'll just say y prime. And this is equal to the limit as h approaches 0. And in this case, since y is standing for my function, I'll say y of x plus h minus y of x. Again, y is an output and x is an input. And just like we saw when we were running through some problems in 2.7, now I'm just plugging in what's in parentheses in for x in my function. So I had m times x, but in my first function I'm going to have m times x plus h. And then y of x is just going to be, oh, I forgot my b. So m times x plus h plus b. And then minus y of x, which is just the function we have, mx plus b. And then all of this divided by h. Multiplying everything out, I get mx plus mh plus b, and then minus mx minus b, all in the numerator. Notice what we see to happen in the numerator. We get some cancellation of terms, like mx and minus mx are going to cancel out, and then so is b and minus b. So all we are left with is the limit as h approaches 0 of m times h divided by h. Just like we saw in examples in 2.7, we get cancellation of the h's. I didn't have to factor this time. But what I end up with is the limit as h approaches 0 of just a constant m that doesn't have anything to do with h. So one of our limit laws was that just gives us the constant. And notice what we get here. The derivative y prime is equal to m, the slope of the function that we started with. Because remember, y equal mx plus b is a line with slope m. So we just got from the definition confirmation of what we noticed in the example above. So y prime is equal to m, which really is just a horizontal line at the value m. So then as far as the domain, the function y equal mx plus b is a linear function, which means it's a polynomial. Its domain is all real numbers. Negative infinity to infinity. And the derivative is also a line. It's a horizontal line. And its domain is also all real numbers. That's something that we'll keep in mind, just how the domains of the function relates to the domains of the derivative. So moving on, here's another example where again we're going to practice using this definition of the derivative. This comes from page 154 of our textbook. Example 3, if f of x is equal to the square root of x, find the derivative of f. And again, we're going to state the domain of f prime. Notice here the domain of this function is x greater than or equal to 0. We can't have negatives inside of the square root. So f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. I'm just restating the definition. Now I'm going to plug into my function. So I did have the square root of x, but now with f of x plus h, it has to be the square root of x plus h. And then I subtract f of x, which is the square root of x, and divide all of that by h. And if you were to plug in h equals 0 right away here with direct substitution and continuity concepts, we would get 0 over 0. So there is a way to simplify this. And the way that that is done is by multiplying the numerator and denominator by what's called the conjugate. This relates to rationalizing something that is involving square roots. So I'm going to multiply by the square root of x plus h plus the square root of x. And I have to do that in the denominator as well. I'm not going to multiply out the denominator. I'm going to leave it factored as h times what we see in parentheses there. But in the numerator, I do need to use the FOIL method. So for example, I have square root of x plus h that will be multiplied by another square root of x plus h. The square roots just cancel. And then I would also have the square root of x plus h times the square root of x, but you also notice that we'll have a negative square root of x times the square root of x plus h. So I would have those two products, but one of them is positive and the other one is negative, so they are going to cancel each other out. And then finally what's left is the negative square root of x times the positive square root of x gives me a negative, and then the square roots cancel out, and I'm just left with x. So this is why we multiplied by the conjugate. We get this simplification. So the positive product and the negative product, they add up to 0. And you'll also notice that we have a positive x here and a negative x there. They're also going to add up to 0. So all that I have left in the numerator is that h, which is good because then that will cancel with the h that's in the denominator. So I end up with the limit as h approaches 0. Notice I still have that limit that I keep writing along these steps. You want to do that as well. And then in the denominator, I have the square root of x plus h plus the square root of x. And now when I plug in h equals 0, because I can use direct substitution and continuity, I get 1 divided by the square root of x plus 0 plus the square root of x. And this gives me 1 divided by 2 of those square root of x's. And I'm just going to leave it like that. I don't need to worry about having a square root in the denominator. And leaving it like this is actually beneficial for us in a calculus class because we may do something more of that function later on. So now, what is the domain of this function? We still can't put negatives in for x, but notice this time we can't put 0 in for x. So here we have x has to be strictly greater than 0. So there is a somewhat relation to the original function we started with, but there is a slight adjustment just depending on, well, we've got a brand new function and we can't divide by 0. So now that we've seen a couple of examples, there are many different ways to write the derivative f prime of x. You can see these also on page 157 of your book. So we've already seen that I've written it as y prime. You can also write the derivative as dy dx. That's the way that I say this fraction. And it looks like a fraction, but we don't want to think of it that way yet. That will become important towards the end of chapter 3 and then also later on into chapter 5. And the way that you want to interpret that is like this. The derivative of y with respect to x. Y is the output, so you're taking the derivative of that with respect to the input x. You can also write a similar notation as d dx of f of x. And this says the derivative with respect to x, that's what that d dx is saying, of, that's the square bracket, the function f of x. And then finally, these last two are mentioned in your book, but we don't really see those in this class, but you will later on if you take Math 84, using capital D to stand for a derivative operator. So next, similar to continuity, we have the ideas of differentiable at a point and differentiable on an open interval. So this definition says a function f is differentiable at a, meaning you can take the derivative of it at a value a, if f prime of a exists, which means that limit that's part of the definition exists. It is differentiable on an open interval a to b, or a to infinity, or negative infinity to a, or negative infinity to infinity, if it is differentiable at every number in the interval. So now let's look at a good example to see where a function may not be differentiable. This is example 5 on page 156, and it deals with the function f of x equal the absolute value of x. The absolute value function has a shape of a v. And hopefully we recognize that from pre-calculus or even algebra. So if x is greater than 0, then we're looking at the right hand of this graph. Then we can actually interpret the absolute value function as just a linear function, x. It's got a positive slope because it's going up and to the right. So for h really small, the absolute value of x plus h is also just x plus h. That's how that works with the right-hand side of this graph. So then for values of x that are greater than 0, the derivative of f of x, f prime of x, is equal to, here's our definition again, limit as h approaches 0 of f of x plus h minus f of x divided by h, which, using what we just noticed in our underlined parts here, that becomes x plus h, because the absolute value of x plus h is just equal to x plus h, and then minus x, because the absolute value of x is equal to x, which then simplifies because the x values can cancel each other out, and then so can the h values, and we're just left with the limit as h approaches 0 of 1, which is 1, which should make sense to us, right? Because the derivative of a linear function just gives you the slope, which is positive 1. However, if x is less than 0, then the absolute value of x actually becomes the linear function negative x, which should first of all make sense because it has to have a negative slope. It's going down and to the right. But also, if you did an example just to verify this, the absolute value of negative 5, using what I wrote right here, should be negative of negative 5, which just turns out to be 5, which we know is true because the absolute value of negative 5 is 5. It tells you the distance that negative 5 is from 0. So then in a similar fashion, for a very small value of h, the absolute value of x plus h becomes negative, parentheses x plus h. So then if we use our definition of the derivative for x less than 0, we end up with the limit as h approaches 0 of f of x plus h minus f of x divided by h. That gives us negative parentheses x plus h minus negative x, just by using what I detailed in the point above, all divided by h. And when we combine like terms in the numerator, you'll have the x's cancel out, but then you'll have a negative h divided by a positive h in the denominator, which gives us a negative 1. And so then the derivative is equal to negative 1, which again should make sense because our function is going down and to the right. So what we have seen is that f of x equal the absolute value of x is differentiable for all x greater than 0 and all x less than 0. So then the one remaining question is it differentiable at x equals 0? We run into a problem. And the problem is with the left and right hand limits. If we think of the logic that we just saw above, we will have that the left and right hand limits at 0 will not be equal. And that's because on one side, as you approach it from the right, it's 1, and as you approach it from the left, it's negative 1. Therefore, the limit does not exist at x equals 0. And if the limit doesn't exist, that means that the derivative does not exist. So f of x equal the absolute value of x is not differentiable at x equals 0. And in fact, in light of the problem that we started off this lecture with, the one from 2.7, the graph of the derivative in this particular case would be a piecewise function again. We'd have, for x less than 0, the slope was -1. But then the moment it crossed over x equals 0, it becomes +1. So we get a jump in the function. And because of that, that's why we have this idea of the limit doesn't exist there. And that also means that the derivative does not exist there. Okay, to follow up from this, there is a way to make a statement about differentiability and continuity, and it is this theorem. If f is differentiable at a point A, then that will guarantee that f is continuous at A. And what I want us to notice is that example 5 shows us that the opposite is not true. If you have continuity, that does not guarantee differentiability. We saw that with the absolute value function. But the theorem that we have here says if the function is differentiable, then that does guarantee that it is continuous. So how can a function not be differentiable? Here's some examples. First, if a function has a corner or a kink in its graph, that's like what we saw in example 5, that's a corner, then it is not differentiable at those corners. If f is not continuous at a point, then that will say that it's not differentiable there. And then finally, if f has a vertical tangent line, then it is not differentiable at that point. So like imagine you had a circle and you focused on some point on the left, you would get a vertical tangent line there. The reason why it's not differentiable at that point is because the slope is infinity, which is the result of the limit. And remember, if the limit is infinity, that means the limit does not exist, so therefore the derivative does not exist. And so then finally, higher derivatives. Since we've treated f prime of x as its own function, then it may have its own derivative as well. And we call this the second derivative. The notation we use is either f double prime of x, or in this case, if we're using this dy dx notation, we have d, which looks like it has an exponent, to y, and that's just saying the second derivative of y with respect to x. In general, we can interpret the second derivative as the rate of change of a rate of change. And also, if the first derivative of a position function is the velocity function, then the second derivative of the position function is the acceleration function, which is itself the derivative of the velocity function. So notationally, we can say that as the second derivative of the position function is equal to the first derivative of the velocity function, and that gives you the acceleration function. So let's look at one final example. This comes from number 55 on page 164. F of x equal 2x squared minus x cubed. And we're actually going to be finding a bunch of derivatives, the first, second, third, and fourth. And I have this note here, higher derivatives. We just keep using the same logic and notation as we had from before. The only change is any derivative above the third starts to have what looks like an exponent in parentheses to indicate the derivative. And we're going to use the definition for this. So f prime is the limit as h approaches 0 of f of x plus h minus f of x divided by h. And again, plugging into my function, I have 2x squared. That will now become 2 times parentheses x plus h squared, and then minus x cubed, that will be x plus h cubed, and then minus f of x, which is 2x squared minus x cubed. and then all divided by h. So now I need to expand everything out. So I have 2 times x plus h squared. X plus h squared is x squared plus 2xh plus h squared. I could use a cubic formula for x plus h cubed, but how about I just peel off one of those x plus h's, and then I'll square the other two, just like I did before. And then I can use the distributive property to finish that. And then I'll distribute the negative that's in between the brackets to get minus 2x squared plus x cubed. This is all divided by h, and I forgot to write my limit. So now I'll just keep expanding the limit as h approaches 0. I'll multiply everything by 2 with this first parenthesis, 2x squared plus 4xh plus 2h squared. And then minus, I'm going to keep all this in parentheses for now, x cubed plus 2x squared h plus h squared x plus hx squared plus 2xh squared plus h cubed. And then at the end here, minus 2x squared plus x cubed. Okay, let's see if we can start canceling some things out. So, for example, I've got a positive x cubed here that will cancel with this x cubed because of the minus. So those are going to go away. And I also have this minus 2x squared here. That'll cancel with this x squared. And as far as the other terms, we might want to start adding some things up first before we cancel those out. So I've got 4xh plus 2h squared, and then I distribute my minus 2x squared h minus h squared x minus hx squared minus 2xh squared minus h cubed. We have some stuff that we'll be able to add up. So I'll do that. Like this negative 2x squared h will combine with this negative hx squared. I just have the products reversed. And in a similar fashion, the negative h squared x will combine with the negative 2xh squared, and that'll be it. So we'll go ahead and add those up. 4xh plus 2h squared minus 3, and I'll write it as x squared h, and then minus another 3xh squared minus h cubed. So now we can see that we can factor out an h from all this stuff in my numerator. And I get h times 4x plus 2h minus 3x squared minus 3xh minus h squared, all divided by h. Those h's will cancel out. And we get the limit as h approaches 0 of 4x plus 2h minus 3x squared minus 3xh minus h squared. And now I can plug in 0 for h. And when I do that, I'm just going to get 4x plus 0, because 2h will become 2 times 0, minus 3x squared, minus 0 again, because 3x times 0 is 0, and then minus 0 squared, or 0. And that means that our derivative, f prime of x, is equal to 4x minus 3x squared. So one thing I want you to keep in mind, just in this intermediate step here, we still have a few more derivatives to find. We started with a cubic polynomial, and the first derivative became a quadratic. So it's gone down 1 degree. I'll also say, if you're starting to think, boy, this is becoming pretty long, the next chapter we start getting some shortcuts. So you will be asked to find derivatives using the definition, but then as we make our way through chapter 3, things do get easier. So now let's find the second derivative of x. This just means the derivative with respect to x of f prime of x, which means we need to find the limit as h approaches 0 of f prime evaluated at x plus h minus f prime of x divided by h, which means we'll have the limit as h approaches 0 of 4 times x plus h minus 3 times x plus h quantity squared minus f prime of x, which is 4x minus 3x squared. All of this divided by h, which gives us the limit as h approaches 0 of 4x plus 4h minus 3 times x squared plus 2xh plus h squared minus 4x plus 3x squared. Already I have some stuff that will be able to cancel out, this 4x and that minus 4x. And then when I distribute the negative 3, I'm going to be able to cancel out with that positive 3x squared, so we can ignore this piece of that distribution. And what I get is the limit as h approaches 0 of 4h minus 3 times 2xh, that's minus 6xh, and then minus 3 times h squared. And now we can see that we can factor out an h. Now I can cancel out the h's by division, and I'm left with the limit as h approaches 0 of 4 minus 6x minus 3h. Now I can plug in 0 for h, and we get that the second derivative of f with respect to x, notice it's a linear function. So we started with a cubic. The first derivative is a quadratic. The second derivative is a linear function. So now the third derivative. Do we really need to use the definition at this point? We've seen a few linear functions so far. It's just going to be the slope of the line. And then how about the fourth derivative? The third derivative is also a line. It's a line that really has equation y equal negative 6. It's a horizontal line. So what's the derivative or the slope of a horizontal line? It's 0. This is the slope of the horizontal line. Which was the third derivative. So now you have all of your derivatives notated. What I would recommend that you do from this point, now take these functions, and there is an instruction in the question to graph them all on the same coordinate plane. And I want you to take a look at that graph. You can use Desmos for this. You don't have to turn this in, but just something for you to investigate. After you've finished looking at all the calculations here, see how the graphs might relate to each other. That'll become important to us as we move on into chapter 3. But one important note is we started with a cubic. First derivative was a quadratic. Third derivative was a linear. So we keep going down by degree. Third derivative is also linear, but notice its degree is 0. And then finally, the fourth derivative is actually the number 0. And if we took any more derivatives after that, it would just stay as 0. So that's an important pattern to notice. That'll become important to us also in section 3.1.